talk about pulsar wind nebulae, talking about the supersonic cases here and what AXIS can do in the next era. So the most important parameter affecting pulsar wind nebula appearance is the Mach number, and that's the ratio of the pulsar velocity to the speed of sound in the ambient medium. Pulsars get their kicks from supernova explosions, which are asymmetric. So they get imparted with a velocity of about 100 kilometers per second or a few hundred on that order. So after a few tens of kiloyears, pulsars, for the first few tens of kiloyears, pulsars move subsonically in the hot SNR interiors where the sound speed is high. And in this kind of environment, we can see the anisotropy of the wind, which manifests as jets and torus usually, tracing the rotational symmetry of the pulsar's spin. But after a few tens of kiloyears, the pulsar exits the supernova remnant, and in the ISM, interstellar medium, the sound speed is usually on the order of tens of kilometers per second. So at that point, pulsars are supersonic. So for most of their lives, the rest of their lives really, they're in the supersonic phase. Supersonic pulsars encounter ramp pressure from the interstellar medium, and that deforms their anisotropic outflows to various extents, and it confines the pulsar wind to within the bow shock and then to parsec scale tails behind them. Mildly supersonic motion results in the jets and the torus being bent back, and highly supersonic motion results in these outflows getting completely crushed and mixed together. So to get a sense of the population here, currently there's about 100 pulsars with X-ray nebulae. About 30% of these, or 30%, are clearly supersonic based on the morphology of the nebula. It's likely that more of these, or most of these, are supersonic, since pulsars only exist in the subsonic phase for a small fraction of their lives. But AXIS will be able to detect nebulae from the fainter ones and grow the supersonic population. So here's an illustration of a bow shock nebula, and below it is a Chandra image of one. All the images I'll be showing are Chandra images, just so you know. So the forward, or the bow shock, confines the shocked interstellar medium, and that in turn confines the shocked pulsar wind. The shocked pulsar wind emits synchrotron radiation, which we often see in X-rays and sometimes radio. Now, for typical pulsar velocities, e-dots, and distances of a few kiloparsecs, these bow shock heads are typically on the order of tens of arc seconds, and their tails are typically a few arc minutes long. The bow shock standoff distance, which is between the pulsar and the apex of the bow shock, is given by this equation here, and it's typically a few arc seconds. So this highlights the need for AXIS's high resolution, which is needed to resolve these arc second scale structures in pulsar bow shocks. So why do we study these? On large scales, supersonic nebulae and their tails are basically one-dimensional structures. So we can easily model how the wind changes and evolves with distance from the pulsar, or with time if you assume the constant velocity of the outflow. They're free from the hot thermal plasma seen in supernova remnants or reverse shocks, which can deform the nebula, as we've seen in previous talks. They can probe the interstellar medium. We can infer its temperature, magnetic field, and gas and dust absorption. And they're also relevant to TeV astronomy, as pulsars are the most numerous class of identified galactic TeV sources. In this talk, I'll focus on the synchrotron emission produced by the pulsar wind, but the same pulsar wind also produces the inverse Compton emission that we frequently see as galactic TeV sources. So understanding how these nebulae wind evolves can help us model galactic TeV sources as well. So many fast-moving pulsars have these compact bow shock nebulae with arc-second scale features, so high resolution is needed if you want to, for example, resolve a pulsar embedded in bright nebula, which is like in the case of the Mushroom and Mouse Nebula. We can separate the pulsar from its nebular emission. We can measure the bow shock standoff distance, which is an important parameter in estimating the pulsar velocity when a direct measurement of the proper motion isn't possible. And again, knowing the pulsar velocity is the most important parameter in understanding what we're seeing in the nebula. And we can also identify the outflow components. We can resolve the jets and the tori and study their emissions separately. So in the first two images, we see torus-dominated bow shocks. Now, these deformed tori usually look like a flattened bullet. So from the geometry, we can constrain the viewing angle from these. And we can tell what angle we're viewing the system from. In the mushroom pulsar nebula, we're viewing it from above, like looking down into the jets, which are then superimposed over the crushed torus. For the mouse, we're looking at it from about 20 degrees off the equatorial plane. And then for these last two, we're looking at them from near the equatorial plane. So why does that matter? Being able to determine the geometry of the nebula and the viewing angle has important implications for modeling of pulsar magnetospheres. Pulsar pulse profiles, shown here, are primarily determined by two angles. The viewing angle, which is zeta, and that's between the spin axis and our line of sight, and the magnetic inclination angle, alpha, which is between the spin and magnetic axis. These also affect the nebula appearance, namely the relative strengths of the jets and tori. Small alpha or closely aligned rotators are going to be jet-dominated, whereas large alpha are going to be torus-dominated nebulae. But what I want to say is that competing models of the magnetospheric emission, like polar cap, the slot gap, and the outer gap models, allow for degeneracies between zeta and alpha for pulse profiles of the same shape. So just by looking at these pulsar light curves, you can't reliably tell what the viewing angle is. However, if you resolve the small scale structure of the nebula, it's really the only way to constrain or measure the viewing angle, zeta, which then allows us to break the degeneracies and test these models. Now, this can also be done for subsonic nebulae, which are still in their supernovae, by fitting ellipses to the tori, but supersonic pulsars are far more numerous. So by expanding this population, we can get more, we can expand the sample of, known viewing angles and test this model across a larger sample of pulsars. So the compact bow shock heads are often accompanied by pulsar tails. These are large parsec scale pressure-confined outflows which trail the pulsar. Shown here are three of the brightest and thus most well-studied ones, as seen by Chandra. Structurally, they're all similar, but spectrally, they are not. In the mouse here, we can see the photon index increasing with distance from the pulsar. Within one parsec, it substantially cools due to synchrotron energy losses, which is expected. In BO355 and J1509, we do not see cooling, even up to many parsecs away from the pulsar. Perhaps this is due to a lower magnetic field in the tail, but already we can see that not all pulsar tails appear the same. These nice data sets, though, come at a high cost. Hundreds of kiloseconds of Chandra time are required to collect enough counts to study these very faint objects. The other tails are even fainter and require more time. So this makes advancing this field difficult without spending megaseconds of Chandra time. But with Axis, its effective area will be between 6 and 8 times that of Chandra, so it should collect counts 6 to 8 times faster, which will allow us to study these for a larger sample with significantly smaller exposures on the order of 50 to 100 kiloseconds. So we can do high-quality studies of about half of the currently known supersonic pulsar population. Now, when we get a lot of counts from a nebula, we can produce spatially resolved spectral maps. With them, we can measure the spectra of particles injected into the nebula before synchrotron cooling occurs. We can characterize how the electron population, or electron and positron population, evolves at distance and time as it moves away from the pulsar, and we can detect phenomena that would otherwise be invisible in typical counts images. For example, in Vela, we can see that there's a reacceleration site happening in the spectral map in an otherwise faint and seemingly uninteresting region. In G21.5, it looks somewhat isotropic, but the nebula is spectrally anisotropic. This is easy to do with the brighter subsonic nebulae, but it's not really possible for supersonic nebula without megasecond Chandra exposures. This is the mouse here. This is the best one we can do. But the spatial elements are really too large here to do anything meaningful with this. But Axis will allow us to spectrally map about a dozen or so pulsar tails with much shorter exposures on the order of 100 kiloseconds or two. So as Oleg mentioned, around a handful of fast-moving pulsars, Chandra has found these faint, columnated parsec scale structures that are strongly misaligned from the pulsar's velocity. They appear unaffected by the ram pressure. They don't bend. All except for these top two are very faint. They have taken hundreds of kiloseconds just to even detect. They're all asymmetric or one-sided, and this is unlike the pulsar jets, which we know these are not pulsar jets because we can see the jets here. But these outflows kind of just break our assumptions of MHD theory, which suggests that the wind should be contained within the bow shocks. So again, these are challenging to study because it requires hundreds of kiloseconds to even detect, and maybe even a megasecond to study these in detail. But AXIS can change this. So what are these? The short answer is that when the gyro radii of high energy particles exceeds the bow shock standoff distance, the particles can't be contained within the bow shock. So they travel along the interstellar magnetic field lines and illuminate them. So no radio emission is seen from these, while their tails are, which supports this theory that only high energy particles are escaping. In reality, it's likely that what's happening here is a little bit more complex. Magnetic reconnection is needed to explain the one-sidedness of the outflows, and that's because in only one hemisphere of the nebula will the magnetic field direction be opposing that of the ISM magnetic field, which is what you need to have reconnection. And then through the reconnected magnetic field lines, the particles can escape. So this just shows how the discovery of these features has sparked a lot of theoretical and simulation work. So AXIS detecting and characterizing more of these will help us better understand these features, and with more objects, we can thoroughly test these models. So zooming in on the Lighthouse Nebula, which is again the brightest one, it's also the most distant at 8 kiloparsecs. We can see that these outflows exhibit arc-second scale substructures. Here we can see the magnetic field draping around the bow shock apex, which is similar to the magnetic draping effect, which is sometimes seen around galaxy clusters, but on a scale millions of times larger. The Lighthouse Nebula also shows evidence of parallel thread-like filaments, which might be similar to those synchrotron filaments we see in supernova remnants, but we haven't really studied these in depth yet. But with AXIS's ability to observe count rates about 7 to 8 times higher than Chandra, we'll be able to study the known outflows in detail and detect even more of these without having to spend megaseconds per each object. So that concludes my talk. Again, AXIS will let us study the larger and fainter fraction of the pulsar tail population, produce detailed spectral maps, discern their geometry and viewing angles, and study these intriguing misaligned outflows. And again, I'll show you an AXIS simulated observation that illustrates the high quality data we can obtain here with reasonable exposures. AXIS will let us map the spectra of these outflows in high resolution 2Ds and with much smaller uncertainties in gamma. So that concludes my talk.
Question? Chris. Thanks. A somewhat naive question. I mean, these beautiful connections into the large-scale magnetic fields. Why does it pick that particular magnetic field line? Is it that there's a pre-existing magnetic filament there, or is it some uniform field, and for some reason it just connects onto that one line?
So that's a good question. So we think that this is just the ambient magnetic field line in the interstellar medium that just happens to be there in that part of the galaxy. Most of these are in the galactic plane, but if you zoom in on the Lighthouse Nebula, it looks like they're individual field lines. So it looks like the pulsar might connect to one, eject a lot of particles into it, but then as it moves through the ISM, starts illuminating another one. So it might just be sequentially illuminating clusters of field lines. Does that answer your question?
Yeah, sort of.
Yeah. It's very interesting, and we need more of these to study. Like there's currently a 700 kilosecond Chandra observation that'll be collected over the next 3 years, and we hope to see how these lines change as the pulsar moves through them. Will it start to illuminate a new one? Do the lines move with the pulsar? But that should help answer our question But again, we need 700 milliseconds of Chandra time to do this. Axis could do that in 100. Time allocation committees are a lot more likely to give out smaller chunks of time like that.
Great. In the interest of time, because we have a bunch of talks in this session, I think we'll move along to the next one. But thank you very much, Noel. Let's thank the speaker again. Oh, sorry.
But if you have questions, feel free to email me.
Great. Awesome. Great. So next up, we have Rebecca Kyer, who's going to tell us about transitional millisecond pulsars. Take it away.
Thank you. My name is Rebecca Kyer. I'm a PhD candidate at Michigan State University. And I have since December been a part of the Compact Objects and Supernova Remnants Science Working Group for Access, and I've had the opportunity to lead author the science case for access to unlock the rapid X-ray variability of transitional millisecond pulsars. So today I'll be talking to you a little bit about my recently published first PhD paper on these systems, as well as what Access can do for them. Okay, so a transitional millisecond pulsar, if you were looking really, really closely at one of the plots that Greg showed earlier, they were mentioned. I was excited by that. These are systems that are a old, rapidly rotating neutron star in a close binary with a low mass hydrogen-rich companion. And they've been observed, they get their name because they have been observed to transition between two really distinct and mutually exclusive states. One is the radial pulsar rotation-powered state, in which we see a bright millisecond radial pulsar active, and there are no signs of accretion. And then it can transition on the timescale of just 3 to 4 weeks to a subluminous accretion disk state, in which this looks very much like a low mass X-ray binary. Let me scoot this over a little bit. This looks very much like a low mass X-ray binary, except for some quirks, which I'll get into. But accretion disk is very much present and active, and the radial pulsar is not. So somehow accretion is quenching or suppressing or blocking the radial pulsar. And so this graphic was made to illustrate the transitions of the really prototypical TMSP, which is the brightest and most well-observed source, which we've seen in these mutually exclusive states at these different times, and has been in the disk state since 2013. And these are some of the properties I say close by. These are all galactic sources because they are so faint. But these are some things about that source. So we do a lot of comparing to the phenomenology of this prototypical source when we're looking for more of them. I should also mention, we call these systems the missing link because in the recycling model of millisecond pulsar formation, transitional millisecond pulsars are toward the end of pulsar recycling. They're no longer actually being spun up by the companion, but an accretion disk can be present at times for years, but then also be unstable and disappear for years. So these are really rare, interesting probes of accretion physics and the interaction, all the complex interactions happening in this very tight binary. So they are very much multi-wavelength sources. Also, as Greg mentioned, they're part of this compact binary zoo. So there's a lot of interactions that are multi-wavelength, but I'll focus on X-ray signatures for this meeting. And I should also mention, I'm only talking about the disk state at this point. So they are also X-ray sources when they are in the radial pulsar state. They look like redback spider binary pulsars, if you're familiar with those. But it's much fainter in the X-ray. It's a different emission mechanism. But there is another science case coming out in the booklet in, I think, June that talks about that state. So this is all entirely for the disk state when it looks like a low mass X-ray binary-ish. The really hallmark of these systems is this bimodal emission level switching, which we call X-ray moding. So this is showing an XMM Newton light curve. If we just ignore the green flaring for now, if we focus on the blue high mode and the red highlighted low mode, these sources are really persistent at an X-ray high mode and then drop within 10 to 30 seconds to a persistent low mode, 7 times fainter, depending on the source, which can last for tens of minutes. And so this is the only system in the universe, correct me if you know of another system that exhibits this type of phenomenology on this timescale. These are the only systems in the universe to exhibit this behavior. So we can look for that really specific behavior to identify disk state candidate TMSPs that we haven't yet seen transition, but we expect to. But there are also some other very unique X-ray signatures of these sources. As you saw in the green part that I asked you to ignore before, they also exhibit really strong X-ray flaring, as well as we've identified some systems which are entirely dominated by that X-ray flaring. And so this is another XMM Newton light curve taken some years after that first one of the same source, exhibiting some of those strong X-ray flares. We've also caught X-ray pulsations at the spin period of the neutron star that are not consistent with being a hotspot. So we don't actually believe that these systems are any material is reaching the surface. And so they've been detected as UV pulsations and optical pulsations, and are really kind of a mystery. But because of how faint they are, these have only been able to be studied in this nearest by source, and we really require something like AXIS to search for those signatures in further away sources. They have a consistent spectral shape, even with really high signal data. A thermal or other model is never a better fit than an absorbed power law, and they have a really consistent power law shape. This helps us identify, even from mean X-ray data where we don't have good time resolution, good candidate sources. And I mentioned that they are subluminous. So their mean X-ray luminosity is about 10 to the 33, 10 to the 34 ergs per second, which is more like a quiescent neutron star low mass X-ray binary, rather than something that has a very bright active accretion disk. So we call them subluminous for that reason. The subject of my first PhD paper was to identify more of these candidate systems. So briefly, that looks like this is part of the game of following up unassociated Fermi-Lat gamma ray sources. So we look at those huge gamma ray error ellipses. We look for bright X-ray sources within them or faint X-ray sources within them among any archival data. So we like leveraging X-ray archival data is a really big part of what I think about. Within those X-ray error ellipses, we look for variable optical sources and follow those up with photometry and spectroscopy in the optical with the SOAR telescope in Chile. And so following this process has yielded 2 new candidate disk state transitional millisecond pulsars associated with these 2 Fermi-Lat sources. At worst, even if they aren't TMSPs, I'm pretty sure they are newly identified faint galactic compact binaries with very bright and highly variable accretion disks that are persistent. They have X-ray spectra consistent with the other TMSPs. We believe they're the most likely associations for these Fermi sources. And in order to have time to talk about AXIS, I will leave any more discussion of that to my paper with the QR code that I'll have at the end as well. I encourage you to look at it and check it out. It has a lot of X-ray data, also a lot of optical data, if that's something that's interesting to you. And just to highlight some of that data is a really cool optical light curve that we obtained of the second source, showing this really high amplitude optical flickering due to instabilities in the accretion disk. But one of the coolest light curves I've reduced in my PhD work so far. Okay, so to understand the rest of the talk, we have to understand that TMSPs are both intrinsically and apparently very faint and very rare. So this is showing optical versus X-ray brightness for all of the galactic field disk state TMSPs. My 2 new sources are highlighted in these pink circles, very faint. And there are only 3 systems which we have actively observed in these 2 mutually exclusive states, one of which is in a globular cluster. So the 2 confirmed systems are these brighter nearby dots here. But that leaves us with 7 really strong candidates. We say candidate TMSP in a really rigorous sense. They've been well vetted with a lot of multi-wavelength data. We don't believe they're accreting white dwarfs or something else. But until they exhibit a real transition, we call them candidates. But from these 9 sources in the galactic field, we estimated that these represent about only 10 to 20% of TMSPs that are within 8 kiloparsecs of us to be discovered. But we really need, because they're so faint, a facility like AXIS to discover and, more importantly, to characterize them and search for signatures like the X-ray moding. That brings us to our science case for AXIS, which will be on the archive in June, I believe. We want to discover more of these systems, characterize their variability, and catch a state change in action would be really cool because the transition of forming or dissipating an accretion disk has been observed by Fermi-Lat, but I don't think it's been observed directly in X-rays so far. So with that TOO response, we could sample that transition over the course of a couple weeks and directly study that in the X-rays for the first time with AXIS. So I will give an example of what AXIS can do for the X-ray moding characterization by talking about one of the sources from my paper. So this source was caught serendipitously in an XMM Newton observation of a nearby CV, and it's really not an ideal observation. It's off axis. It's missed by one of the MOS cameras. And it's not a chip gap of one of the PN cameras, so it's not great. But even so, we simulated what moding in the prototypical source would look like at the flux level of this source, and you would see maybe a handful of longer-lived low modes of the system. But maybe these are low modes. We highlight them here, but it really the X-ray data for the source is not sufficient to say whether the system is moding or not. We can say it's not X-ray flaring in this observation. But we need something, a higher sensitivity observation to distinguish those cases. So we simulated what the moding in the source or moding in the prototypical source would look like as seen by AXIS at the flux level of the source. And we would definitely be able to see it if it's there. And so this histogram is showing that bimodality of the count rates in the light curve. So AXIS would absolutely be able to do it. Thanks. So I'm starting out my summary. I hope I've convinced you that these are really cool and vital test beds of accretion and the interaction, the close interactions between all the components of these systems. They are probing the ends of recycling and are important for understanding the different phases that neutron millisecond pulsars go through in being spun up. They display unique phenomenology in the X-ray, as well as at other wavelengths that I haven't had time to get into, but they are very faint and rare. We've presented 2 new candidates, but AXIS will really be necessary to, the high effective area of AXIS is really necessary to fully characterize even the systems we already have discovered, as well as we can leverage all the improvements that AXIS brings from time sensitivity to spatial resolution to unlock these signatures in dense environments like the galactic centering and globular clusters. And there's also a lot of really incredible synergies with current and upcoming surveys and efforts. So that's where I'll leave it. Thank you.
Thank you very much. Do we have any questions? Yes, Kim.
For JO639.1, I'm just curious, was that the subject of the XMM observation? Why was it off axis? And did you use the PN or the MOS data for that light curve?
Yeah, so it was not the target of that XMM observation. It was an observation by Gianluca Israel targeting a CV in the field. That's pretty far from the X-ray source that we proposed as the counterpart. We used the MOS2 counts to fit the spectrum and the flux to not worry about whether the chip gap is affecting something. But then we find that there isn't a significant difference in spectral shape between the PN and the MOS2, and then combine them for the light curve. Simulated them separately and then added them and with the window function at the end, which I hope is the appropriate way to do it.
One more question. We'll go with Greg.
So given that TMSPs are an intrinsically older population, is the secret to finding them blind surveys, or is it really targeted follow-up of candidates from other wavelengths or past surveys?
Yeah, I think that having an X-ray error circle to look for an optical variable counterpart is really the key. And so if we had something like DSA 2000, we could use with microjansky sensitivity, then we could start using radio surveys to look for these sources. But currently there's not a survey that has microjansky sensitivity that covers a lot of these regions. So we really do rely on X-ray first, and then to whittle down the optical potential counterparts and follow up from there.
I'll follow up, so I'll ask him to call it.
Thank you.
Great. Great. Let's thank Rebecca again. While they're getting ready, just to introduce, we have Tyler Holland-Ashford, who's going to tell us about measuring neutron star velocities with AXIS, building upon the legacy of Chandra. Go for it.
Great. Yeah, thank you. So also thanks to the speakers in the first session for providing a lot of the background on supernova remnants and neutron stars and their connections, allowing me to skip over some of the background here. So neutron stars, the compact objects left over from some core collapse supernova, have been observed to have these velocities of hundreds of kilometers per second as they move through space. And these velocities are too fast to come from the disruption of any progenitor binary, indicating that they are a result of the explosion processes themselves. The supernova explosions accelerate these neutron stars to these hundreds of kilometers per second. And there have been a few theories about how these exactly are formed, and they seem to relate to the asymmetries of the explosion, that the neutron star is kicked either opposite the bulk neutrino asymmetries. Most of the neutrinos move one way, neutron stars kick the opposite way, or the neutron star moves opposite the bulk ejecta. The bulk of ejecta moves one way, the neutron star moves the other. Most evidence seems to have now favored that second scenario, the neutron star moving opposite ejecta, although there still remains possibilities that in certain cases, strong enough neutrino asymmetries can cause the neutron star kick in that opposite direction. And a reason to look at neutron stars and try to understand and constrain their velocities is to compare them to supernova remnants, the properties of remnants, their asymmetries, their energies, in order to learn more about the explosion processes themselves and correlate neutron star velocities to maybe energy of the supernova or the progenitor type to try to learn more. These is just showing a sample of remnants, just showing their different levels of asymmetries, large and small scales. And Laura Lopez in 2009 found that core collapse remnants are more asymmetric, more support for these strong asymmetries, generating both ejecta asymmetries in the remnant, and then also these neutron star kick velocities. And so simulations have successfully generated neutron star velocities of a few hundreds of kilometers per second in a variety of remnant cases and supernova cases. Here, just showing a neutron star on the left moving up, and the bulk of ejecta, I think this is a simulation of Cas A from Wong with Thanarat, moving down. So again, that anti-correlation between neutron star and ejecta, and then simulations by Burroughs in 2023 were able to accelerate neutron stars to hundreds to maybe thousands, low thousands kilometers per second. And you can see here there's some type of correlation maybe that you can draw between the progenitor mass and the final neutron star velocity. Observationally, similar things have been found by myself and others. In supernova remnants, the neutron star seems to be observationally moving opposite the bulk of ejecta. And this is shown by the green arrows here moving toward the ejecta, and the white is pointing in the direction of the neutron star motion. And even further than that, here's a zoom in of Cassiopeia A, the inner arc minute or so. The neutron star seems to be moving most directly opposite to the heaviest elements, the ones formed in the deepest layers of the star, closest in proximity to the neutron star. Here, if you just draw a line from the neutron star to the explosion site and then back evolve that, you see it's most opposite these heavier elements, your iron, your titanium, your calcium, as opposed to the lighter elements, oxygen and silicon. And so the key point here of a lot of my research has been to actually measure these neutron star velocities. And a simple way to do so, the most straightforward way, is to just watch them as they move over multi-epoch data, measuring their proper motions. This is conceptually simple, but in practice difficult, because neutron stars moving a few hundreds kilometers per second at distances of a few kiloparsecs will only move about 0.2 arc seconds or so per decade. So you really need 10 or more years between observations in order to get any type of constraint on these velocities. Here, for example, is showing the measurement of the neutron star in Puppis A over a span of 7 to 20 years. And you can see that the errors, the uncertainties on that first measurement from 1999, 2006 are pretty large. And also the velocity estimate is very high because any small uncertainty you have, any offset that's created by imperfect astrometry will tend to bias the measurement to larger values. And so you really need measurements over these long 10, 20 years to crack down on that error and get robust velocity measurements. There's also another way of measuring neutron star velocities. If you figure out the supernova remnant center, which you can't just assume is the geometric center. You can't just draw a circle around the remnant and kind of shrink that to its circle, to its central point, because remnants are inherently asymmetric. So if you're doing that, you're asserting some level of asymmetry. But if you look at a whole many different ejecta knots throughout the remnant and measure their expansions through time, then you can back evolve all of them to a central location, giving you the explosion site. And then if you have the age of the supernova remnant, you have explosion site, current location of neutron star, time between those two, giving you a velocity. This can be easier in that the ejecta knots are typically moving faster than the neutron star, so you don't necessarily need as long of a baseline. But then, of course, you still have to measure all these precisely and back evolve them to a central location. And from this right plot here, you can see that you can get a pretty uncertain estimate of that explosion site, depending on how many knots you can identify and how well you can back evolve their motion. And so these are a couple ways of measuring neutron stars, but going back to proper motions, and really even the ejecta knots methods, is that only Chandra has the necessary spatial illusion, that arc-second, sub-arc-second spatial resolution, in order to measure the motion of the neutron stars over the baselines that we have. Here is just showing a sample of different supernova remnants observed by Chandra. And the issues that come with using Chandra data, two pretty much, is that Chandra has a large off-axis PSF. So these plots are just showing the size and the shape and the orientation of the PSF as you go further off-axis and in different directions compared to the aim point. And this makes it more difficult. Of course, you need the neutron star to be close to the aim point in order to have a small PSF and resolve its position precisely. But then you also need to be able to use registration sources to calibrate Chandra's astrometry, because the astrometric solution of Chandra is only accurate to about 0.5 arc seconds, which is larger than that expected neutron star offset over 10 years, 20 years. And so you need to correct for that. This is done typically by finding registration sources with finding sources that you know the positions for, and then using that to solve for the actual true astrometry of the image by creating some transformation matrix, changing the observed astrometry, the default astrometric solution to the true astrometric solution. And typically, the best sources for these are Gaia sources. If you can find any X-ray sources in your field of view that match with Gaia sources, those have precisely known positions and precisely known motions, so you can know where they should be at any time period, and then you transform your image of what it is into the positions that it should be based on these Gaia sources. But because of that PSF problem, all of these registration sources need to be within a few arc minutes of the aim point of Chandra, else their PSF starts getting too distorted and you can't measure their positions to enough precision to actually use them to correct astrometry. But you can do, this has been done, myself and others have done this for different epoch data, finding different point sources in Chandra images. Here are a sample of a few different neutron stars and a few different remnants. And the neutron star is indicated in different colors in different image, but then all the other sources are calibration sources that you can identify in the Chandra image, link to a known Gaia star, and then use that to correct the astrometry. And by doing that, you can get offset uncertainties of 0.1 arcs second, 0.05 to 0.15 are the typical scales that have been found, essentially depending on how many of these registration sources you can find. For example, on the left here, Cassiopeia A was only able to find 5 sources within a close enough to the aim point. But for something like G11.2 over here, you can find 10, 20, maybe even 30 registration sources. And the more you have, the better. And so here is just a table of that I've compiled of literature, neutron star velocities, specifically neutron stars that are associated with supernova remnants. So you compare those neutron star velocities to supernova remnants. And the key takeaway for here is that there's not that many of them. I mean, there's 20-ish neutron stars associated with supernova remnants that have velocities measured, but of those, only 8 or so have emission from the remnant being thermal and thus reflecting ejecta. So you can directly compare the neutron star velocity to the ejecta properties of the supernova remnant. And so finally, this brings us to AXIS and all the great things that it will do. So just very straightforward, AXIS observations in the 2030s will provide a 30-year baseline between it and early epoch Chandra observations, allowing us to measure neutron star offsets of neutron star motions over those longer baselines. Over those baselines, neutron stars should move about 0.1 to 3 arc seconds, which should be enough for AXIS to observe for most of these neutron stars. And then also importantly is that AXIS will have a much larger field of view of Chandra, specifically a field of view with a relatively small PSF, PSF of under 2 arc seconds. There'll be about 10 times larger of field of view than Chandra. And then similarly, AXIS with its pixel size smaller than its PSF will be able to localize these point sources to sub arc second accuracy. And so using both of those combined with the fact that AXIS will have much greater effective area at energies below 1 keV, which is where these Gaia sources, which are mostly bright and optical but have shock wind energy, that have emission from their winds shocking their surroundings of temperatures of about 0.5-ish keV, so fairly soft. And so you really need that low energy effective area in order to observe these sources. And so with AXIS, we'll be able to detect many, many more of these registration sources in order to calibrate the astrometry and then use these very long baselines between AXIS and Chandra observations to obtain more neutron star velocities and obtain a large sample so we can identify trends in neutron star velocity and explosion energy, explosion type, and other properties. Thank you.
All right, thank you very much. Do you have any questions?
Thank you, Tyler, for very nice talk. And the question would be about how necessary it is to have X-ray images of supernova remnants to play this game of comparing asymmetry to the direction of pulsar motion, or can you use radio images of supernova remnants to some extent to do that or not?
Great question. Yeah. So X-ray images are important for looking at supernova remnants because you can get that ejecta emission, that millions of degrees temperature ejecta, and so you can compare that to that tells you about the results of the explosion dynamics, the ejecta properties as they're expanding outward. Radio, I understand, is more about the shell emission. That's typically what you get more of in radio, which would then be heavily influenced by the environment. So that could still be very useful. Looking at the environment of explosions can help inform you about progenitor winds and such. And so linking the neutron star velocity to the winds to the progenitor type can still be useful, but they look at different things.
Any other questions? I've got one, which is do you have any way of estimating what the projection of the motion on the sky is?
So the neutron star, the redshift of the neutron star, is it moving?
Exactly. Yeah. How much the motion is along the line of sight versus projected?
Yeah. So all of this I've talked about in 2D transverse velocities, moving left and right. For measuring line of sight velocities for neutron stars, that's hard. They don't have lines really that you can measure the Doppler shifts of. But you can infer a velocity by knowing that if you go from the assumption, which seems to be mostly correct, that neutron stars move opposite the bulk of ejecta, then if you can identify the bulk red or blue shift of the ejecta, then that can tell you at least whether the neutron star is likely moving toward or away from you. And theoretically, if we get enough data points that allows you to fit a relationship between like ejecta asymmetry, the magnitude of ejecta asymmetries, and the magnitude of neutron star kicks, you could turn that of the magnitude of the ejecta that is red shifted versus blue shifted into a magnitude of a kick.
Right.
And so that's been done. Adrian Piquino did that with the analysis of Cassiopeia A, finding that I think the bulk ejecta in the direction opposite of the neutron star was redshifted, which implies that the neutron star is blue shifted coming toward us.
Great. Thank you very much. All right. So let's thank Tyler again for a very nice talk. While we're getting ready, just for introduction, we have Pragati Pradhan, who's going to tell us about stellar wind studies of high mass stars in binary systems.
Hi, so today I'm going to be talking about massive stars. We all know that massive stars most of them are in binary systems. So I'm going to be talking about massive stars in binary systems, focusing specifically on two kinds of systems. So we have when you have a massive star surrounding along with in orbit with a compact object, in this case, a neutron star. We call those as high mass X-ray binaries. And I'm going to be talking about high mass X-ray binaries a little bit, and also on the other kind of massive star systems, binaries basically, which has two massive stars that are orbiting around each other, which you call the colliding wind binaries. So I'm going to be focusing first on high mass X-ray binaries right here. But before I talk about the specific properties of high mass X-ray binaries, I want to zoom out a little bit and talk about the population of high mass X-ray binaries in general, in context to access. So, so the angular resolution of access obviously is going to be really, really important to look at galaxies, and I'm specifically proposing for like low luminosity Asian galaxies that are within the local group. So here I have in the sample a group of six galaxies, which are basically low luminosity Asian galaxies, which means like they don't have a really bright Asian at the center. They have been looked at with eROSITA, they've looked at many of them, but only these were like bright enough for, kind of detailed spectral analysis with eROSITA. But obviously we know that, there's a lot of point confusion when we're talking about observations with the eROSITA, so which access can definitely mitigate. So the rationale behind actually observing low luminosity Asian will be leveraging on the sensitivity of access. And at the same time, also because there are so many of them compared to the high luminosity Asian galaxies. So by number, they win because that gives us more information about the universe in general. And case in point is this galaxy right here, NGC 2903. This has been observed many times with Chandra. It has a maybe 250 or 300 kiloseconds observation with Chandra. Now, again, the galaxies that I showed earlier were like, they are, I would say, good candidates because they are, relatively face-on, X-ray bright. They also have great multi-wavelength coverage. So if you want to, identify the optical companion and things like that, and there are many point sources that have been detected in NGC 2903, along with some potential ULXs that will be of interest to many people here. So just zooming in, this is what SDSS image looks like to the left, and if you zoom in now to the right, you will see the Chandra image of the same galaxy right there. And Arash actually helped me do the simulations for access, and we see that for a fraction, 1/5 of the Chandra time, you're going to get the same resolution, same kind of signal to noise ratio with as you would see with Chandra right there. So on the left is the simulation for 50 kiloseconds, actually 1/5 of Chandra time. And this will actually be really interesting because if we talk about synergies, then UX has a, I found this up on a paper, forgot to put a reference right there, but it's actually aiming to look for like low metallicity galaxies. And when we talk about high mass X-ray binaries, low metallicity, that's where you actually expect to find them in case of low metallicity galaxies. So I'm actually really interested to look at the population of high mass X-ray binaries in general, the luminosity function in the low luminosity end, because, it has implications not only to enrich the universe, but also, they act as great ionizing sources for the early universe and so on. So that makes it really interesting and a great discovery science for access. Now zooming on, the other thing I'm really excited about, now I'm focusing from like a wider population of high-mix binaries to individual ones. I'm also excited about the possibility of having like, kind of continuous observations. So here I show on the left plot right here, and this right here is the schematic for a high-mass binary SENX3. But what you basically see right here is, this is the coverage with Chandra over this half orbit. It's a short 2-day period, so it's possible to do that. So you see a lot of variability, already really structured light curves in this in the system right here, and this kind of extra variability. Can be, it's a topic of great interest. It can be, either caused by, for example, clumps in the accretion wind. You can have clumps which are not accreted, and then that leads to, it acts as a foreground, between the neutron star and the observer, causing variations in the intensity, extra intensity, but also clumps that are accreted, they kind of like change the accretion regime, and that causes variability as well. And in order to disentangle this kind of variability, you have to really look into like very very smaller time scales, and it is indeed possible to do this with axis. For example, the typical coherence timescale for this kind of clumps will be, depends on system to system, will be typically like a few kiloseconds, for example, and axis will actually be able to probe much further. So this is a simulation for a similar kind of system for 500 seconds that you'll be able to probe with axis. So it's going to really be able to measure the really smaller clumps and find out characterize the clump. The case in point right here is, for example, this is from XMM right here again, which is great for observing, like having uninterrupted absorptions right here. So if you focus on this, this part of this simulation right here, you see how over a matter of like 20 kiloseconds, the burst basically rises and also just vanishes. So we really need fast response time in order to capture this kind of transients. These are also high-mass X-ray binaries, but they are a slightly different class, which you call the super Chen fast X-ray transients, and they basically share similar properties with normal, if there is anything like normal high-mass X-ray binaries, but basically very very fast response time, large orders of luminosity changes between peak and quiescence, which makes them stand out. And you'll be, by looking at the time resolved spectroscopy, it was able to, we were able to determine what is the mass and the clump of the a neutron star, a clump of the clump in the stellar wind, and but the problem with doing, right now in this field is like, when we determine clumps this way versus like clumps which are determined using, I don't know, radio and other observations, there's an order of magnitude difference. So we need to really understand this, characterize these clumps, because without understanding, really understanding the characteristics of these clumps, it becomes difficult to understand the evolution of massive stars in general, because that drives the mass loss rates. Now, I'm also very excited about the fast response time and the possibility of, having an onboard transient detection in AXIS, because I personally spent like 2 years at Penn State exploring the possibility of detecting, having onboard transient detection in the Athena wide field imager, and I left the details right here. But long story short, it was, practically, it was very much possible to do that. So I'm excited at this possibility myself. Going back, I wanted to also just point out that it's also a right time for the clump science that I was talking about, because now we have like promising hydro simulations right here, which kind of like so it's like a feedback between the observing team and the simulation team, and now it's the right time to actually compare our observations with the simulations and vice versa. So I'm excited at this possibility. And in the 2 minutes or 3 minutes I have left right here, I just want to talk about, specifically about colliding wind binaries. And like I said, these colliding wind binaries are, two massive stars. And they have very powerful winds, and in this case, different from high-mass X-ray binaries because both of them are massive stars. In this particular simulation, one of them is a Wolf-Rayet and the other is O star. That leads to that kind of a bow shock forming around the star with a weaker wind. But the interesting thing about this is it kind of like shows. So it becomes really important to understand, kind of like photometry in X-rays basically, because depending on the orbital separation, you would expect, depending on how the light curve varies, And these are like really long period systems. For example, I put in typical scales for like 2 colliding binaries right here. So it becomes really interesting to understand how the light curve varies over, over many decades. And so over many years. And for example, what I hope with Axis is if we manage to look at, for example, this kind of like superstar clusters. I show this the example of Westerland 1 right here that has recently been looked at with Chandra again, and numerous sources detected right there. But also the really interesting thing that was seen in this was, there were point sources which look like massive stars. And with Axis, not only will you be able to distinguish like the individual sources right there, but also that what was completely missed out in Chandra is because of the absence of soft response below 1 to 2 kV. It is really impossible to disentangle the soft excess. Now, so I show, and these kind of systems, they have a very variable spectra, like you can see right here. This is for another colliding binary syn with XMM, but they are very, very variable. And the importance of just having the soft X-ray excess below 2 keV, look at having to looking at the soft excess over different orbital phases will basically let us know if that where the emission is originating. Is it in the for example embedded wind shocks or contributions from individual massive stars and stuff like that. So those are the possibilities. And so these are the 5 pillars of Axis that I'm most looking forward to. Now I am also actively involved in high resolution spectroscopy. So in addition to all the things that Axis can provide, I also look forward to synergy for high X-ray spectral resolution. And I end my talk right here.
Cool. Wonderful. Thanks very much. Do we have any questions? Yeah, Mike.
So I might ask you about actually the Athena transient alert monitor that you mentioned you had done a lot of work on. I was just curious. I mean, you have with Athena, you have a larger field of view, and so you're going to have a lot of sources. Like, how does that exactly work when you could have all sorts of things in there to sort of identify? Like, are you looking at sort of a range of timescales or how?
Okay, so with Athena, what we did was we kind of like so we kind of looked for 2 different things. One was like whether we'll be able to detect new transients, for example. And the way we would do that was, initially how it was proposed was, and this was before Rosetta was put in a safe mode, was to have like a catalog on board. So let's say a catalog of all the sources along with RATech and the limits in which they were originally discovered. So we put in like an onboard catalog, and the idea was to have like a processor right there that will be able to take all of this. And then my job was to write an algorithm that will basically tell you so what I did was I did some 60 simulation, assuming the wide field image or characteristics and stuff like that. I took the Chandra deep field survey as an example and plugged in a random sources right there. And our main job was to find out whether we'll be able to like detect new sources, but at the same time, if we'll be able to detect variability as well. So we found out that, if we kind of think of, I don't know, maybe 30 sources, 30 counts as detection, then we'll be able to look for variability in matter of less than 1 kiloseconds. So something like that. And the whole processing time was like I was working on a very old laptop. It was like 100 seconds. So that was translated onto like the CPU processors that would be eventually be used on board. That would make it even faster. But yeah, that's very promising.
Great. Any more questions? I've got one, which is you mentioned that the flare you saw in the binary looks like it's due to accreting some clump in the wind. Is there? I'm curious what the reasoning is that it's due to hitting some part of the wind and not instead some. I mean, I know these things don't have the same sort of persistent disks necessarily that we think of in other X-ray binaries, but I'm wondering if there's some kind of instability in the accretion process that could produce that rather than the neutron star going through a clumpy wind.
Yeah, that's a very important point, and definitely like the rationale behind Like why we think this is, this is like an interception by a clump event is because we only kind of see changes in absorption. So we kind of say, because there are only changes in absorption and the total continuum remains the same, it's probably just the software is being absorbed, and that is what we explain as clump events. But there are definitely cases like those. For example, I'm looking at a symbiotic X-ray binary right now, where you see this kind of like clump event situations, but also where you have this variability, but the whole continuum goes up and down. So it's not like due to absorption, definitely. So there, in that case, there has to be some instability set on. So yeah, so basically like absorption versus whether the whole continuum goes up and down. And if it's a pulsar, it additionally helps because when there is like, for example, the onset of propeller regime, then you would expect no pulsations. So.
Great. Okay, let's thank Pragati very much again. Next up, we have Stephen Chen, who's going to tell us about multi-wavelength analysis of a globular cluster X-ray sources. All set?
Hello.
Great. Take it away.
Hi, I'm Stephen Chen. I'm a graduate student working with Oleg Kargozov at George Washington University. I'm here to present my multi-wavelength analysis of X-ray sources in globular clusters. So globular clusters, for those of you that are unfamiliar, are massive and old star clusters living on the outskirts of galaxies. There are many compact object systems discovered in these star clusters with Chandra and HSD. And importantly, we need the high angular resolution of these missions because the star density in globular clusters is very high. However, we still have over 1,000 Chandra sources that's not been classified yet in globular clusters, partially because each of them may have upwards of like 10 Hubble counterparts. And this motivates a machine learning classification approach, especially since recently we are getting new multi-wavelength surveys from JWST and Meerkat in the radio. I'll be focusing on the globular cluster Omega Cen, which is the largest globular cluster in the Milky Way that's been extensively covered. And it has a somewhat unique formation history in that it might have been a dwarf galaxy at birth. So this is our machine learning, multi-wavelength machine learning pipeline. It's based on a random forest classifier, and we include many multi-wavelength features from a variety of surveys to use as features. We do many processing steps in the pipeline to make the results as free of bias as possible, including we sample feature uncertainties multiple times to make the measurement uncertainties be reflected in the classification results. I encourage you to see the poster by Yi Chao for other applications of our pipeline. So to do supervised machine learning of X-ray sources in globular clusters, we need a training data set. So I've collected about 300 classified sources in globular clusters, 25 globular clusters. And when possible, I've also cross-matched them to Hubble counterparts. So here is a summary of the sources in my training data set and the percent of them that have counterparts. You see that only a quarter of the known MSPs in globular clusters have Hubble counterparts, which makes classifying them with our pipeline a bit more difficult. So our general methodology is to first use a probabilistic cross-matching of X-ray sources to Hubble sources using N-way, and that outputs for each association of X-ray sources to Hubble sources, the probability that that association is true. And we classify using our machine learning pipeline each association separately, because depending on which counterpart, the classification can change drastically. Aside from the Chandra features, we are also using features from 5 Hubble filters that's been extensively covered, that has extensive coverage in many globular clusters. And we also have a suite of independent information, some of which are very recently acquired, that we can use to verify these machine learning classification results. So here is a summary of the classification performance of our pipeline. This is showing leave one out evaluation on the training dataset. Basically, the more diagonal this matrix is, the better it is for that class. So, for example, the classification performance for AGNs and QLMXPs as well as active binaries are pretty good, but for CVs and millisecond pulsars, they are worse, partially because the millisecond pulsars, they don't have a lot of counterparts. So to focus on my investigation of omega sen, this globular cluster has more than 200 Chandra sources, 16 of which are cross-matched to background galaxies identified with optical proper motion. And upon manual analysis, we see that most of them are the true counterparts. And that implies that these X-ray sources are AGN. However, some of these AGN are bright, and therefore they look very similar to CVs in both the X-ray and optical. And so they were classified as CVs by both past papers as well as our pipeline. We can distinguish them from real CVs is H alpha, but previously and currently in many other globular clusters, H alpha Hubble coverage is still poor, so we cannot use it in our pipeline yet. So right now, mu class cannot reliably identify the correct counterpart for unclassified X-ray sources by itself, because it's missing crucial information, including proper motion. However, we can at least get the number of the number of expected true counterparts from the excess density close to Chandra sources at small separations from Chandra sources. So for example, for background galaxies, there's clearly an excess density of background galaxies at very small separations, 0.1, 0.2 arcseconds away from Chandra sources. And we can only do this again because we have proper motion measurements that these are indeed background galaxies and not cluster members. So we can also do this for the proper motion identified cluster members. And we see that we expect an excess of 75, up to 75 sources, which implies that about 75 optical counterparts can be identified for the X-ray sources. And so out of these expected counterparts, we have, again, the proper motion selected background galaxies, about 14 giant stars, which are likely to be coronally active because of some reason that's not very well known yet in the literature. About 10 sources with H alpha excess, which includes 6 previously identified CVs and 1 previously identified candidate CB, but now we can confirm because we have proper motion measurements, as well as about 30 other main sequence stars that are likely to be active binaries. And now with this new information, we are able to classify a majority of Chandra sources with Hubble coverage. And so here's just C and D is showing on the left, previously known and candidate CBs. They are blowwords of the main sequence in the red here. And here we see giant stars near the top of the main sequence that are likely to be true counterparts to X-ray sources. We also have recently acquired Meerkat radio images and catalogs at sub-arc-second resolution, similar to Chandra. But there's many more Meerkat sources in the Chandra field of view than Chandra sources. Importantly, there's about 30 Meerkat sources expected to be associated with the cluster, and many of those are not cross-matched to Chandra within 3 arc minutes of this cluster center. Of the 77 sources in the whole field of view cross-matched to Chandra sources, 6 are probably background galaxies because of optical proper motion. 10 are cross-matched to soft X-ray sources, implying that they are likely MSPs, and the remaining are likely AGN, but there's no optical counterpart with matching proper motions. And so here is the Meerkat image with Meerkat sources in the red. Overlaid on top in the green are Chandra sources, and we see even near the cluster center, there are many faint Meerkat sources that are not cross-matched yet. So this is showing X-ray luminosity versus hardness ratio of Chandra sources cross-matched with Meerkat sources. And in the left here are again the soft X-ray sources, which include both known and new candidate MSPs in this circle. And we also have recent JWST observations. And I think my impression is that there's not much infrared observation of globular clusters. So these are new. What we can do is we can make SEDs all the way from the UV on the left here to the mid-infrared in the right with these new observations. And these 2 SEDs are known CVs in the cluster. And we see in the clear H-alpha axis here. And these are clearly non-thermal as opposed to the most of the normal main sequence stars. And here also is a source peaking in the blue UV that's cross-matched to a soft X-ray source, and it's also cross-matched to a Meerkat source. So this is one of the candidate MSPs that we found. And here's some other examples of very weird non-thermal SEDs. We don't know if they're associated with the X-ray sources yet. We need more work to be done on that. But our main takeaway is that to classify the large population of faint X-ray sources in globular clusters, we really need a synergy between multi-wavelength surveys at high resolution across the entire spectrum. And while our machine learning approach is useful in finding interesting sources to be looked at in more detail, it can be greatly augmented if we add proper motion information, as well as other multi-wavelength surveys in the radio and infrared, and even time domain information in any or all of these wavelengths. And with these, considering all of this information and analyzing them together, I believe we can systematically classify most of the currently unclassified X-ray sources in globular cluster. And with access, we will probe an order of magnitude deeper in flux and uncover entirely new populations of active binaries, millisecond pulsars, including cross matches to currently unassociated radio sources and CBs. And importantly, because of access's effective area, the positional uncertainty of X-ray sources can actually be improved over Chandra, despite its somewhat wider point spread function. And I'll leave you off with a simulated image of the globular cluster 47 talk.
Thank you very much. Question?
Thank you for this talk. This is, an extremely useful tool coming into the future. I wanted to ask if you have any sense of what's the most important tool or, the most important thing that you could use to augment your classification of sources and, like what would help the most? Would you need long time monitoring in infrared with GWST, or what's the one thing that would help classify those sources the most? And that's the first question. And the second one is there a prospect of putting together like a fundamental plane of unclassified X-ray sources where you could say that north of this line everything is an AGN and south of this line everything is a spider pulsar or something like that? Is there a plan or a strategy to reach something like that?
Okay, so I think so for your first question, I think that depends on what you're looking for. If you're trying to just identify cluster members versus background AGN, then proper motion measurements will be the most immediately helpful. If you're more interested in like searching for millisecond pulsars, then I do think, yeah, temporal variability information from longer observations could be very helpful in identifying if there's a binary system that's the most likely counterpart to the X-ray source. And if it's a binary system, then orbital information can be extracted, which can limit what kind of X-ray source this can be. And for your second question, the fundamental plane. One very helpful diagram that's unfortunately not in the presentation is X-ray versus optical luminosity, and that is pretty useful in separating, for example, AGN from normal stellar type sources. But that again depends on which counterpart you're choosing from like the 10 possible counterparts. So we need tools to identify the correct counterpart more.
Time for one more quick one.
So given the source density of globular clusters and the fact that radio bright RCVNs, a type of active binary, also have sort of this soft X-ray spectra, how do you tell apart the RSCVNs in subgiants or even subgiants from millisecond pulsars?
So RCVN radio bright, you're saying?
RSCVN can be fairly radio bright. Matter of fact, we may have marked some things as black hole X-ray binaries that are radio RSCVNs.
And what about subgiants? You're saying they're also radio bright?
Some RSCVNs can be subgiants.
Okay. So right now, the radio data is pretty new to me. I think from what I'm seeing, there's maybe only a few of the giant sources in Omega Sen have radio counterparts, but the millisecond pulsars, most of the millisecond pulsars that I've seen, that's in the training data set, and also the ones I've classified as candidates, are stopping the X-rays, and also they have non-giant counterparts. Only a minority of millisecond pulsars have giant counterparts. So I'm thinking that that will be hard to determine on an individual basis.
Great. Okay, let's thank Stephen again. So our final talk of this session. We have Marina Oreo, who's going to tell us about Novae and how it bursts in X-rays.
Let's go down with the arrows. Okay, so I'm going to talk about novae in outbursts and how to differentiate them with other luminous supersoft X-ray sources that we often observe. The outbursts of novae are due to originally to a thermonuclear runaway. Things are a little bit more complicated, but it's important to remember that the outbursts can happen in three types of systems, both cataclysmic variables, so a white dwarf with a main sequence in a period of less than 2 days, usually just a few hours, and symbiotic stars with periods of a year or more, and a red giant or an AGB star. And in principle, there are claims that there are nova-type phenomena like short thermonuclear flashes observed also in high-mass X-ray binaries, especially with B stars where you can accrete from the debris disk. So X-rays can emit it in three different phases. When the thermonuclear runaway happens and the envelope starts expanding in a sort of almost blue giant configuration, you have first you have only softly critique to optical light, and you have a fireball that expands. It's very soft and luminous. It lasts only for a few hours. Not going to talk about that. Then you have colliding winds, either because you're in a symbiotic, so with a very complex environment, with a red giant, with a nebula disk, and so on, but also because the whole wind phenomenon is not smooth and not spherically symmetric. It's a rather complex phenomenon, and the wind happens not just because of the thermonuclear runaway itself, but because of either radiation pressure driven wind or because you feel both Roche lobes. Then when you start dispersing the absorbing ejecta, you can observe a very luminous super soft X-ray source as long as the burning lasts in shell. So we're talking about systems that are like an AGB stars, where at the bottom of the envelope you ignite in shell, usually hydrogen, sometimes even helium. So the luminosity is very high, it's 10 to 38 ergs per second, but of course this is all due to an effective temperature of even 1,000,000 degrees, but it's very affected by absorption. Anyway, the emitting novae outbursts emitted or wavelength, they're seen at distances, even in X-rays, of up to 10 megaparsecs in directions of low column density. I'll talk about axes now, but first I want to show you the variety of X-ray spectra we obtained with the RGS and with the Chandra gratings. There is a lot of physics. This is just the stellar, the super soft white dwarf continuum with many absorption features and a few emission lines of the ejecta. Great variety, lots of physical phenomena to study. Look at the beginning of the outburst on the left and on the right towards the end of the outburst when we hit a cold and dense clump in the ISM. So in the case on the right, the case on the left can be described as simple collisional equilibrium thermal plasma. Instead, in the case on the right, we think we did, and it's not the only case where we think we had evidence of charge exchange. Look at these radiation recombination continua that are seldom observed. I will go back to what we can do with axes though. And since we don't observe only novae as luminous supersoft X-ray sources, we need to think of ways to differentiate and to try to classify this interesting population. So if you look at the Liu Wang catalog of Chandra AC sources up to 40 megaparsecs, of about between over 11,000 sources, of which only 234 are known AGNs. All the others may be X-ray binaries and supernova remnants. Of these, 450 are luminous supersoft X-ray sources with all the emission below 0.8 keV. And 70 of them are even classified as possible ULXs. So, of course, there is a lot of uncertainty due to the column density. And so the first kind of objects we would like to differentiate are white dwarfs that are burning hydrogen without having a thermonuclear flash, sort of persistent sources, because they're burning in shell, but they radiate all the energy that they are generating at very high mass accretion rates. So they may undergo an accretion-induced collapse, or they're interesting as thermonuclear supernovae progenitors. The plot on the right shows what I did in a paper of 2010, where I looked at all the sources and tried to classify them in M31. And you can see that apart from a few outliers like the supernova remnants and 1AGN that we could determine what they were, only a few were classified as novae. Some of them were persistent, some of them were transient, but it wasn't clear, even looking at the FAT, the HST images, it wasn't possible to really determine what they were. In M31 alone, if you look at the figure on the left, it shows two epochs of M31 observations with ACEs analyzed by the Max Planck group, P. Charbel, and others. And you can see that all the sources with the circle are actually, they were able to determine with optical observations that they were novae. When we look at galaxies even farther away, even outside the local group, then what we have is that it's very, very hard to determine what the optical counterpart or a counterpart at other wavelengths may be. The position is precise, but the PSF in the SES images is very degraded. And even with the position of 1 arc seconds off axis, we cannot really determine what they are. So we will be able to identify many sources with axis instead, off field. And so it will practically open a new era. That's what I claim. Here I looked at, so the other thing that I forgot to mention that was in the slide is that there are also sources that are not white dwarfs, black holes, transients, and it has been claimed also the elusive intermediate mass black holes can look like a nova at large distances, especially if you're not sure about the column density. So at this point, how do we differentiate? Here I try to look at an example taken from similar to what Di Stefano and Liu did when they claimed they had found one of these extreme supersource sources looked like an intermediate mass black hole. I simulated the spectrum observed with axis, sort of cheated because there is no background, but this one is at 6 megaparsecs, and you can see that if you try to fit an atmosphere, the one in red, it does look different. I mean, it's not a big, your chi-square may still be good, but you can tell that it's different from a black body. So this is sort of an extreme case. Of course, if you have more, better quality, you can do better. Now, I mean, a shorter distance, especially in the local group, you would do a lot better. You will see some features. Coupling this with the repeated exposure, so what I'm advocating for is a sort of repeated survey, monitoring of some nearby galaxies every few weeks, sometimes every week, or sometimes every month, in order to differentiate the temporal behavior, to see which sources are persistent, which sources temporally may look like black hole transients. And that would be very important because we would have a classification of novae in X-rays and be able to link the super soft X-ray phase with the other parameters that in the models are connected. And with abundances and population ages, because we know in what kind of galaxies we're finding them. And the onset time, the effective temperature, all of this is dependent on abundances. So we need to have some benchmarks to define the models better. Two more things that we can do with axis for novae. First of all, uninterrupted exposures will allow a kind of timing that would be very important for us. We detect pulsations of novae in the super soft X-ray phases with periods, especially in the hottest, more luminous ones, periods of minutes or even of 30 seconds. So the shortest periods have been claimed to be due to stellar pulsations, probably to the burning itself, but nobody has been able to model it yet. Rich Townsend in Wisconsin has tried, but gets shorter periods than 30 seconds. Then the other periods seem to be due to rotation, to the spin. It's not clear why we would see the rotating white dwarfs when everything is such a hot mess around it. But it's interesting to understand the physics, to know what these periods really are. And the shorter periods have been claimed to be pulsations because there seems to be a drift in the period. They seem to be rather QPOs. But then we found out recently that if you have a long, see that periodogram, Worley et al., if we have a long period of time, about 10 kiloseconds, we can get rid of the effect of the varying amplitude, which when you do Lone Scarger analysis causes a sort of effect, a drift that is not really there. And so NICER has been great to detect this period. SIFT is good too, but the exposure times of 1,000 seconds are really not good enough. We need to determine what these periods really are. We have to do an analysis with longer exposures to get rid of this artifact of the varying amplitude. One more thing, resolving no remnants in X-rays can be challenging, but it has been done for the largest and most supernova remnant-like one. This is from a paper of Ballman, 2005. There was a follow-up also with Chandra 2009. And it is extremely interesting, of course, to see a nova remnant, like a little supernova remnant with all the shocks and interaction with the interstellar medium, and try to understand what the elements are there. So Axis will widen this study probably to 5 to 10 remnants, we think. We try to be on the conservative side, but it is another challenging but really rewarding thing that can be done. And so I'll flash my conclusions. Of course, I didn't talk about Novae accreting sources. Cataclysmic variables will also be observed as accreting sources. Symbiotics have a nebula that emits X-rays, and so it's going to be very, very interesting also from that point of view.
Thank you very much. Any questions?
Thank you. Yeah, just a simple question. The simulation of the supersoft source at 6 megaparsecs, what was the exposure time that was assumed for that?
I wrote it there, I think. Just a second.
Sorry if I missed it.
I think it was 10 kiloseconds.
Okay. Okay.
Probably optimistic. There was no background.
But for 10 kiloseconds, we wouldn't actually expect much background to be kicking in. So that's, it's probably not a huge problem to ignore background for this. Yeah.
Oh.
Thank you, Marina. So I was wondering, for the periodic features that you observe for the QPOs, what are the frequencies for those? And what about the drift that you see? Do you also see some change in the frequencies for the drift? For the drift that you mentioned at the end? And the frequencies are? Oh.
So the periods are 35 seconds, a couple of them, another 89 seconds, and we see the drift by a second. So, but that would be typical of stellar pulsation, when we can have different modes overlapping, or we can have retroradical. So the way to tell is to be able to do very sophisticated analysis where you can tell whether this is really constant or not.
Yeah, thank you.
Okay, I think that brings us to lunch.